We're going to talk about section 3.9 in our book, which our book calls the tangent line approximation, and which is also known as the linearization of f. So we say that differentiable functions are locally linear. That's an important idea in AP Calculus. What that means, if you graph, you can see an example of it. If you graph y equals x squared on your calculator, you're going to get something that looks like this. Then if you hit the zoom button on the top row and then arrow down to zoom in and hit enter again, you'll see on the bottom of the screen, it'll say 0, 0, x equals 0 and y equals 0. So it's put the cursor right at the origin. If you hit enter again, it's going to zoom in on that same place. So that's the first time we hit enter. Hit enter again, and you can see that parabola start to flatten out. Hit it a third time, and now you can see it's starting to really flatten out. Let's go one more time. The fourth time you can barely see it because what you're seeing is now we're hugging that x-axis there. It's almost become a horizontal line. Of course, if you hit window, you can see we're really zoomed in a lot because the x value that I'm seeing, the x min is like negative 0.039 and the x max is 0.039. So we're really zoomed in close around there, but around that point there, because it's differentiable, it is actually looking like a line. In fact, it's looking like the tangent line of the curve at that place. Now, if you try doing that with something that is not differentiable, for example, if you did that with an absolute value of x function, then you can try that over again and zoom in all you like around there, and it's never really going to change much. It's never going to look like a line because it's not differentiable. The absolute value of x is not differentiable there, therefore it is not locally linear. So in the next few days, we're going to talk about the fact that a tangent line is a good approximation to the actual function, and then simpler to use because it's just a line, as long as we don't go very far away from the point of tangency. So the further away we go, the poorer approximation it will be. So let's see, now it says here in the next part in the green, if f of x is differentiable at x equals a, then L of x is equal to f of a plus f prime of a times x minus a is known as the linearization of f at a. So that's the words that we will use. And we'll sometimes use that notation that we're going to call L of x, the linearization of f of x, and that's an approximator. That's what we're going to use to approximate it. X equals a is the center of the approximation. Now, some of that language is kind of maybe a little confusing and overwhelming. It's really, what this is here is no different than just our tangent line. So if we have some function, y equals f of x, and then we pick any point that we like, say call that x equals a, then when we run that up to the curve, its y-coordinate is going to be f of a, which is going to make that point there on the curve be a comma f of a. We know that the slope of a tangent line to that curve is the derivative evaluated at a. So if we're talking about the equation of that tangent line, it's going to be y minus the y-coordinate of that point, which we said is f of a, is equal to the slope, which we said is f prime of a, times x minus a. And then if we just add that f of a to the other side, that's exactly what we're saying is the linearization. So it may look really abstract and kind of exotic, but really this is something we've done quite a bit of already. We can find the tangent line to a curve, and then we can use that to approximate values of the curve that are somewhere close to the x value of the point of tangency. Let's see what an example of this is going to look like. So let's find the linearization of f of x equals the square root of 1 minus x at x equals 0, and then use it to approximate the square root of 1.02 without a calculator. So to find a linearization means to find the tangent line. And to find a tangent line, we need a point and we need the slope. They're telling us the x value of the point is 0. If we plug 0 into the function, we'll get the square root of 1, which is 1. That's going to be our point. To find the slope, we know we're going to take the derivative and then evaluate that at x equals 0. So this is a chain rule derivative, but a pretty mild chain rule derivative. So it's going to be 1/2 times 1 plus x to the negative 1/2, and then times the derivative of the inside function, which is just 1. So we can write that maybe in a little more evaluation-friendly form. The 2 from the 1/2 will be in the denominator, and the 1 plus x to the negative 1/2 is just going to be a square root of 1 plus x in the denominator. So that means our slope is going to be f prime of 0, and if we plug in 0, again we get the square root of 1 is 1 times the 2 is 2, which is going to give us a slope of 1/2. Since our point is actually the y-intercept, it's pretty easy to write this in slope-intercept form and say 1/2 x plus 1 is our tangent line, or if we want to give it fancy notation, we could call it L of x, which is the linearization. No different than just finding the tangent line. Now we want to use that tangent line, that linearization, to approximate 1.02. Now, since our original function was the square root of 1 plus x, that means the x value we're going to plug in is the 0.02. Does that make sense? So we are going to find L of 0.02, which means we are going to plug in 0.02 for the x, and then just simplify that. Half of 0.02 is 0.01, plus 1 is going to make that be 1.01. So that's a pretty pain-free way to get an estimate for the square root of 1.02. Now, if you want to see how good an approximation that is, throw it onto your calculator. So on your calculator, if you take the square root of 1.02, I think it's going to say something like 1.00995, and then it's going to go on and on and on. So you can see that if you rounded that to 3 decimal places, at 1.00995, we'd be spot on, because that's exactly what we got just using our tangent line to approximate that. Okay? Now, the further away you go, it's going to be a poorer approximation. You know, if we wanted to use, say, that to approximate the square root of 2, then that would mean this is the square root of 1 plus 1, so our x value would be 1 if the square root of 1 plus x was going to be 2. So if we do our linearization that we had up here, if we do that and put in 1, then we're going to get 1/2 times 1 plus 1 is going to be 1.5. And if you plug in the square root of 2 into your calculator, the square root, let me get that to come up, the square root of 2, I'm getting on my calculator to be about 1.414 and so on. So you can see our error has gotten significantly bigger the further away from the point of tangency x equals 0. Now, another interesting thing, if we want to know, is our approximation going to be an overestimate or an underestimate? This will come up many times. Over or underestimate. Is our tangent line approximation going to be an over or underestimate? Then if we know that the square root of 1 plus x, well, we know the square root of x is that top half of a sideways parabola, and the x plus 1 is going to translate it 1 to the left. So we know that our curve here, our function, f of x equals the square root of 1 plus x, is going to be concave down. That's the big key here. So our tangent line at x equals 0, which we're using to approximate the function, because the original function was concave down, if we want to evaluate it, use the tangent line to approximate the value of the function somewhere other than 0, that means that we are going to come up and use the tangent line as a way of approximating the actual value of the function. We can see that this will be an overestimate. So if the function is concave down, the tangent line approximation, that is the linearization, will be an overestimate. Okay, let's do a couple other examples. I'm going to move to a new panel here. So let's use a linearization. Use a linearization to approximate. I'm going to give us a couple of challenges here. First, we're going to approximate the square root of 123, and then we're going to approximate the cube root of 123. So armed with this little bit of information, we're trying to figure out now, how can we find a tangent line to first approximate this square root of 123? Well, first we got to come up with a function. So what would be a good function to approximate a square root of something? Well, how about a square root of x function? Does that make sense? Then the next thing is, what point should we find the tangent line at if we want it to be fairly close to what we're trying to approximate, that square root of 123? And remember, we want to pick a number where the numbers that we are going to evaluate we can do without a calculator. So we're looking now for a value of x whose square root comes out nice and even and is close to 123. So hopefully you're thinking of 121 because that is 11 squared. So that would mean our point on the curve is going to have an x value of 121, and its y value will be the square root of x, which is the square root of 121, which is 11. Now we're still looking for the tangent line, so we're going to need the slope, and the slope is going to come from the derivative evaluated at our x equals 121. So the derivative is going to be 1/2 x to the negative 1/2, or in a more friendly evaluation form is going to be 1/2 square root of x. So the slope is going to be f prime evaluated at 121, which is going to be 1/2 times the square root of 121, which was 1/2 times 11, which is going to be 1/22, or 1/22. So our tangent line is going to be y minus the y coordinate of our point, which was 11, is equal to our slope 1/22 times x minus 121. Now I'm just going to add the 11 to the other side, but I'm not going to get carried away and try to simplify this a whole lot, because shortly here it's going to become much easier to deal with. We want to approximate the square root of 123. That means our x value is going to be 123. So we're going to, in our linearization, we're going to plug in for x 123 and solve for the y. That will be our approximation to the square root of 123. So we are going to get 11 plus 1/22 times, and the 123 minus 121 is just 2. So that's going to be 11 plus 2/22, which is going to be 11 plus 1/11, and I would just leave it like that. That is going to be our approximation to the square root of 123. Let's try the same idea for b. Now, can you see what our function might be if we are looking for the cube root of 123. Hopefully you're thinking the cube root of x. If we want a nice value of x that's close to 123, but that's easy to evaluate in our cube root function, hopefully you're thinking x is 125. So that will make our point be x will be 125. The y value will be the cube root of 125, which is 5. Our slope is going to come from, for our tangent line, is going to come from the derivative, and the derivative of x to the 1/3 is going to be 1/3 x to the, subtract 1 from the 1/3, and we get negative 2/3, and this might be a little easier if we think of that as 1/3 times the cube root of x squared. So when we plug in our 125, let me do it over here. So our slope is going to be the cube f prime of 125. We're going to get 1/3. We're going to take the cube root of 125, square that. So the cube root of 125 is 5. Squared is 25. That's going to make our slope be 1/75. So our tangent line is going to be y minus the y-coordinate, which was 5, is equal to our slope, which is 1/75, times x minus the x-coordinate, which was the 125. Now we're going to, maybe I'll add the 5 over first. Whoops. Y is 5 plus 1/75 times x minus 125. We want to evaluate this at 123, so our approximation is going to be 5 plus 1/75, and we're going to get 123 minus 125. So that's going to be 5 plus 1/75 times, that's going to be a negative 2. So we're going to get 5 minus 2/75, and hopefully you can see that's 4, and let's see, if I take 2 from 75/75, that's going to be 73/75. That is going to be our approximation to the cube root of 123. Very good.